All right, let's do some multiple choice questions about polar curves. Let's see, which of the following integrals gives the length of this y equals tangent x between x equals a and x equals b, where they're both less than pi over 2. So let's see how we would do that. Oh, there's one piece of information that I need to give you, isn't there? Haha. Okay, I'm going to tell you right now in the notes here. We know how to do parametric and we know how to do polar, but we don't know how to do length of a regular old curve. And that's coming in the notes, and I forgot that I stuck it in here, so I'm going to give you the quick notes of that right now. You can get it real easily from parametric. Remember that the length of a parametric curve from t1 to t2 is dx dt squared plus dy dt squared. Right? Well, look, if you want to take a regular curve, let's say you have y equals tangent x, for example, the easiest way to parameterize this to something that's already in function form, well, that's the same as saying x is just equal to t and y is equal to tangent of t. Right? It's just setting x equal to t and then y equals whatever your function was with a t in it instead. So that's the parametric version of this. So making that swap just in general, if x is equal to t, then dx is the same as dt. So this is just dt dt, which is just 1. So for a regular curve, we end up with the integral from x1 to x2. This just turns into 1, plus dy dt. Well, x is the same as t, so that's just dy dx squared dx. So it turns into this integral, right? This turns into a 1. This turns into the dy dx squared. Okay? So using that idea here, say, what's the derivative of this? It's secant squared x. So the plugging this in, we go from a to b of the first thing should be 1 squared, right? And then secant squared squared. So that would be e. Sorry about that I didn't show you that before, but it just comes straight out of the parametric version. All right. Number 2. Oh boy, is this another one of those? Jeez. Okay, so sorry about that, but hey, you get to try it again now. So y equals natural log of secant x. The derivative of that is 1 over whatever times the derivative of what's inside, which is secant x tangent x. So it looks like the derivative of natural log of secant is actually the tangent function. So from 0 to wherever, that's the derivative. So it's going to be 1 plus tangent squared. Yeah, you look and that doesn't match up to any of these, but then you say, oh, wait a minute. If I take sine squared plus cosine squared equals 1 and divide all those by cosine squared, then I get tangent squared plus 1 is equal to secant squared. So that's equal to secant squared. And the square root of secant squared is just secant. So it's actually a. That's a little bit tricky. 1, because I hadn't told you how to do that yet, and 2, because of that little trig identity. All right. Number 3. Now this looks like something you actually have notes for. The area of region enclosed by the polar curve r equals 1 minus cosine theta is which one of these? So let's see if we can do that. We have the integral from 0 to 2 pi. It's not one of those special circles. We have 1/2 of this squared, 1 minus cosine theta squared d theta. And let me think about that for a second. This is it's gonna involve some kind of trig substitution. So I'm gonna say right now that you can go ahead and use your calculator for this. They don't do this anymore, problems like this, without letting you have your calculator. So I'll have to fix that and say, go ahead and use your calculator for this. Happy about that, John? John March, that is. I'm sure you are. You used your calculator anyway, didn't you? So let's see. Doing that with a calculator, I got 1/2 times math 9, that's fn int, of 1 minus cosine x squared, comma x, comma 0, comma 2 pi. And before I hit enter, I'm just going to go to mode and make sure that I'm in radian mode. So, and that gives me 4.712 blah blah blah. And if you're not sure, like, how many pi's is that? Well, just divide it by pi. Divide by pi. That's 1.5 pi, or in other words, c. All right. So here's another one. Let's see if this is one that we can do without a calculator. Looks like we may need a little bit more room. So the area of the region enclosed by the polar curve r equals sine of 2 theta. Well, we got to think about, oh, they gave us, never mind. I was going to say if that's one of those special cases, but they told us from 0 to pi over 2. So that solves that problem. So we want 1/2 the integral from 0 pi over 2 of sine of 2 theta squared d theta. And it's the same thing again. It's that same trig substitution that you're not going to like what you actually have to do to get a sine squared or a cosine squared out of there. You actually have to use the half angle formula in some form and square both sides of it. So we're not going to go there, so I'm going to go ahead and say you can use your calculator on this one too. So let's see if I can get it. Let me, oops, second entry. Let's see if I can modify this and get it in there. So we want the sine of 2x. I think I got too many parentheses here. Get rid of one of those. From 0 to pi over 2. And that gives me that divided by pi as, oops, I wanted to have wanted this divided by pi. That's going to be 1/8 of a pi, pi over 8. That's what I'm getting for that. All right, you recognize that as 1/8, or math, enter. Hey, it's 1/8. All right, this one, supposedly, you can use your calculator, so let's see. What's the length of the arc from 0 to 3? So the length of again, that's a regular one, so it's another one, that bit that I didn't show you yet. From 0 to 3, we want square root of 1 plus the derivative of this. The derivative of this is just x to the 1/2, looks like, squared. Oh yeah, so you can do this. I don't know why I put calculator there. Well, you could certainly do this without a calculator. Should we do that? Why don't you try doing that? Maybe you already entered it with the calculator, but that's an easy u substitution here. So let's see, I'll go ahead and work it right here. So if you let u equal 1 plus x, then du is equal to dx. And effectively, we just shift this over 1, right? So this is going to turn into the integral from, now my u numbers are 1 to 4, which is nice, those are square roots. And this is going to be the square root of u to the 1/2 du. So that's equal to, the antiderivative of this is 2/3 u to the 3/2. Remember how to do this? And it's 2/3 times u to the 3/2 is, 4 to the 3/2 is 8, and 1 to the 3/2 is 1, so that's 14/3. All right. Again, sorry if that caused some frustration because I hadn't shown you that yet. That should have been in the notes today. Number 6. Which of the following gives the area of the region enclosed by the loop of the graph of the polar curve r equals 4 cosine 3 theta, shown in the figure above? Well, we got to figure out the angles here. Look at our choices. It's either negative pi over 3 to pi over 3 or negative pi over 6 to pi over 6. Just kind of looking, I mean, this looks much more like a negative pi over 6 to pi over 6. But we could do better than just looking. We could really justify that by saying, look, as we look out here to 0, at 0 radians, I'm at, when you plug in 0 in here, you get cosine of 0, which is 1. That's at 4, right? And then as your angles go up, it looks like it's diving back in like this. So where would it be equal to 0? Where does it have a radius back of 0? Well, that would be when the radius is 0. So when does 4 cosine of 3 theta equal 0? Well, divide both sides by 4. That doesn't matter. If we want it to be 0, that has to be 0. And cosine of the angle we're looking for, cosine of pi over 2 is 0. So we're talking about when 3 theta is equal to pi over 2, and that happens when theta is equal to pi over 6. So just by inspection, that gets rid of that and that. So yeah, I think it was Austin in class earlier said, like, when you just looking at that, I mean, it looks like pi over 6, right? So you could probably reason your way to that just by looking. Okay, now, how do we find area? Polar area is 1/2 times the integral of r squared. That's 16 cosine squared 3 theta d theta. And we now know that these are negative pi over 6 to positive pi over 6. And 16 can come out, so that looks like this, right? 16 times 1/2 is 8. Just make sure the other ones, that one they forgot the square, and this one they forgot the 1/2. So E is the correct answer. Good. Not bad. That's what good means. Not bad. Which of the following is equal to the area of the region inside the polar curve, this, and outside the polar curve, that? It might help a little bit here to make a quick sketch of this. These are those circles, right, that we've been talking about, the ones that complete from 0 to pi. So making a real quick sketch of this. Here's theta, here's cosine theta, and this is the other circle, 2 cosine theta. I'm just going to make a quick table of the 4 cardinal points. Pi over 2, pi, 3 pi over 2, and 2 pi. So cosine of 0 is 1, and 2 times that is 2. This would be cosine of pi over 2 is 0, and 2 times that is 0. And then cosine of pi is back to, is negative 1, and that's negative 2, and then it just starts to repeat stuff here. So, well, I guess I'll stop there. So when I'm looking at 0 radians, one of the circles is out here at 1, and the other one's out here at 2. And then by the time you get to pi over 2, it's gone all the way back around to here, and then it makes it back around here. When you're looking in the pi direction, it's negative 1. So the whole circle completes like that from 0 to pi. And this one does the same thing, it's just that big, right? Not surprisingly, circles of this type that are cosine are laid out on the x-axis, right? Because cosine is corresponds to the horizontal or the x-coordinates of things. Okay, so we want the area inside the big one but outside that one. So this is the easy kind, right? This is the kind where it's just going to be the integral from 0 to pi of the area. Now the outside one would be 1/2 of this r squared d theta minus 1/2. We're just going all the way around, right? So those are the same. It's not like that weird one of them's turning into the other one situation that we looked at today. And the other one is just cosine of theta squared. And then we could simplify that a little bit and see if it turns into something. So 1/2, 4, I've got 4 cosine squareds minus another cosine squared. So putting all the integrals together, I get 3 cosine squared theta d theta, and then that can come to the outside. So it looks like 3/2 times cosine squared theta d theta from 0 to pi. Let's see if that's a choice. It's not. So now we have to figure out what that's equivalent to. Here's some things it's not equivalent to. That actually, I think that's the right answer, isn't it? Here, that looks just ours, but it doesn't have the 3/2, so that's not right. Can't be equivalent to this. There's the same as ours, but different limits of integration. That can't be right. Those ones don't have cosine squareds in them. So, well, I guess maybe by elimination you could get this, but let me tell you why this is right, or maybe you can figure it out. Why don't you look at your picture and think about that for a second. Okay, if you're back now, look, as we go from 0 to pi over 2, we get this area, right? And by the symmetry of these circles, this area here is half the total area, right? So that means if we go from 0 to pi over 2 of the same thing, and then just double it, multiply it by 2, so that turns that into a 3 out front. So it's equivalent to A. That's a little tricky. But they like to do tricky things sometimes, the College Board.